All right, get ready to explore the amazing world of optics.
We're diving deep into light, mirrors, and
The
lenses.
stuff that lets us see,
Capture
even
images.
unlock the secrets of the universe
It's really amazing
Mm.
how often we experience these principles.
without even realizing it.
Yeah, every time you look in a mirror, wear glasses, or take a picture,
Oh, yeah, for sure.
you're using the science of how light works.
Okay, so let's start with something I've always wondered about.
Okay.
Rainbows.
Rainbows, all right.
How does a simple rainstorm
Right.
transform the sky
Oh.
into this, breathtaking display of color?
Yeah.
It feels like magic, pure magic.
It does feel magical,
Yeah.
but it's actually all about reflection
Okay.
and refraction.
Yeah.
Two fundamental ways light interacts with stuff.
Okay, reflection and refraction.
Yes.
Those sound familiar, but
Yeah.
remind me,
Yeah.
what exactly are they again?
So imagine throwing a ball at a wall.
Okay.
It bounces back, right?
Yeah.
That's like reflect.
Okay.
Light bouncing off a surface.
Gotcha.
Refraction
Yeah.
is more like if that ball rolled from a smooth surface onto grass,
Uh-huh.
it changes direction a bit
Okay,
because
so-
it's moving between two different mediums.
So with rainbows, we've got light
Yeah.
bouncing around inside raindrops and de-changing direction.
That's right.
But how does that make all those
Okay, so
distinct colors?
this is the cool part.
Okay.
Sunlight,
Mm-hmm.
which looks white to us,
Right.
is actually made up of a whole spectrum of colors,
Whoa.
each with its own wavelength.
Okay.
When light enters a raindrop, it bends
Okay.
or refracts,
Uh-huh.
but different wavelengths bend at slightly different angles.
Oh, okay.
This separates the colors,
Interesting.
like a prism does.
So the raindrop acts like a tiny prism, splitting the white sunlight into its individual colors.
Exactly.
That's amazing.
And then those separated colors,
Yeah.
they hit the back of the raindrop and bounce back, reflect internally, and then
Yeah.
they're refracted again as they leave the raindrop,
Wow.
spreading the colors out even further.
So because this is happening in millions of raindrops,
Yes.
we see that,
Yeah.
magical arc of colors across the sky.
It's amazing.
Right.
Mind blown.
It really is a beautiful example
Yeah.
of how simple principles like reflection and refraction can create something so awe-inspiring.
Totally.
Speaking of reflection, let's talk about mirrors.
All right, let's reflect on mirrors, literally.
Oh, good one.
But first, can we define reflection a bit more formally?
Absolutely.
I just want to make sure I've got the basics,
Of course, yeah. Reflection is basically the bouncing back of light.
Mm-hmm.
When it hits a surface, it can't pass through.
Okay.
And there are two key laws
Right.
that govern how this bouncing happens.
Okay, I'm all ears.
So imagine you're shining a laser pointer at a mirror.
Okay. Yeah.
The angle the light hits the mirror at,
Uh-huh.
we call that the angle of incidence.
It's always equal to the angle it bounces off at,
Okay,
which is the angle of reflection.
gotcha.
Think of it like a perfectly symmetrical bounce.
So it's not just bouncing randomly.
No.
There's an actual law
Yes,
that dictates this perfect symmetry.
precisely. And there's another law to make it even more precise.
Right.
The incoming light ray,
Yeah.
the reflected ray,
Uh-huh.
and an imaginary line perpendicular to the mirror
Okay.
at the point of impact,
Right.
which we call the normal,
Okay.
all lie in the same plane.
Gotcha.
This makes sure that the reflection is predictable.
So even if the mirror is curved or at an angle,
Yes,
those laws of reflection still apply.
they do, absolutely.
Wow.
And that leads us to those funhouse mirrors
Yes.
that can stretch, shrink, or distort your reflection in all sorts of wacky ways.
Right.
Those use curved mirrors, specifically spherical mirrors,
Okay.
which are basically like sections of a sphere.
Okay, so spherical mirrors, those are the heart of funhouse reflection.
Yes.
I'm guessing there are different types of spherical mirrors, right?
You got it. Concave and convex.
Okay.
Concave is like the inside of a bowl.
Okay, curving inwards.
Yes.
Convex mirrors
Yeah.
bulge outwards,
Uh,
kind of like the back of a spoon.
exactly.
And each type creates unique images,
That's right.
depending on where the object is.
Yeah.
So concave curves in, convex curves out.
Yes.
But how do these different shapes affect how they reflect light and form images?
Okay, let's start with concave mirrors.
Okay.
A great example is a makeup mirror
Uh-huh.
or a shaving mirror.
Okay.
They magnify your face because they reflect light inwards.
Yeah.
Towards a single point, the focal point.
Oh, that's why my face looks bigger in those mirrors.
Exactly.
All the light is being focused on one spot.
Precisely.
Crazy.
And the distance between the mirror and that focal point
Uh-huh.
is called the focal length.
Okay.
It's a crucial measurement for understanding how concave mirrors form images.
All right, so Concave mirrors magnify by focusing light.
Yes.
What about convex mirrors? What kind of image magic do they create?
Think about those rearview mirrors in cars.
Okay.
Those are convex mirrors.
Yeah.
Ever notice how they give you a wider view,
Uh-huh.
but make things look smaller?
Yeah, totally. It's like a panoramic view, but everything's miniaturized.
Exactly. That's because they curve outwards,
Uh-huh.
causing light rays to spread out.
Oh, I see.
This gives you a wider field of view,
Right.
which is super important for drivers.
Makes sense.
So they can see more of what's behind them.
So concave mirrors bring light together, magnifying things,
Yes.
while convex mirrors spread it out for a wider view.
That's right.
It all comes down to the shape.
It really does.
Okay, before we move on to lenses,
Okay.
any key takeaways about spherical mirrors we should remember?
Absolutely. Remember, concave mirrors are like light gatherers.
Okay.
They converge light rays to a focal point
Uh-huh.
and can magnify images.
Great.
Convex mirrors
Hmm.
are like light spreaders.
Okay.
They diverge light rays,
Gotcha.
providing a wider field of view,
Right.
but the images appear smaller.
Got it. Concave mirrors for close-ups.
Yes.
Convex mirrors for the big picture.
Exactly.
Now, I know lenses are next,
Yeah.
but I'm still curious about how light actually bends
Okay.
when it passes from one medium to another, like from air to water.
Right.
What's the science behind that?
That's a great question. That takes us to refraction.
Okay.
Essentially, light travels at different speeds in different mediums.
Okay.
When it crosses a boundary between two mediums,
Yeah.
like from air to water, it changes speed,
Uh-huh.
and that causes it to change direction or bend.
So it's like light hits the brakes when it goes from air to water,
That's a pretty good analogy.
causing it to swerve.
Yeah, and the more the speed changes, the more the light bends.
Okay.
The reason light travels at different speeds and different materials
Yeah.
is because of something called the refractive index.
Refractive index. Sounds complicated.
It's not as complex as it sounds.
Okay.
It's a measure of how much a material slows down light
Oh.
compared to a vacuum
Uh-huh.
where light travels at its fastest speed.
Okay, I see.
Water, for example, has a higher refractive index than air.
So that means light slows down more in water.
Exactly.
So the greater the difference in refractive index between two materials,
Yeah.
the more the light bending.
That's right.
Is that why a straw looks broken in a glass of water?
Exactly. The light from the straw
Right.
travels through the air,
Yeah.
then hits the water,
Right.
slows down, and bends,
Okay.
making it look like the straw is broken at the surface.
So it's not actually broken, it's just an optical illusion
Exactly.
caused by the light bending at the boundary between air and water.
Precisely. And this bending is so predictable,
Really?
we can actually calculate it using something called Snell's law,
Okay.
which uses the angle the light hits the surface and the refractive indices of the two materials involved.
So Snell's law basically tells us
Yes,
how much the light will bend when it crosses a boundary
precisely.
between two materials. That's pretty cool.
It is cool.
So we've talked about reflection and refraction,
Yes,
two ways light interacts with matter.
that's right.
And next, we're going to dive into the world of lenses,
Lenses, all right.
which I have a feeling are all about harnessing the power of refraction
Yes.
to do some pretty amazing things.
You're right about that.
Awesome.
You're absolutely right. Lenses are all about refraction. They're these curved pieces of glass or plastic that bend light in specific ways, and they're in everything like eyeglasses, telescopes, cameras, you name it.
Okay, so lenses use refraction to bend light, but in a controlled way.
How does that work?
Well, just like spherical mirrors, lenses come in two main types, convex and concave.
Okay.
A convex lens is thicker in the middle and thinner at the edges, and a concave lens is thinner in the middle and thicker at the edges.
And these shapes determine how they bend the light rays that hit them.
So does a convex lens converge light like a concave mirror?
Yes, exactly.
And a concave lens diverges it like a convex mirror?
You got it.
Okay.
A convex lens brings those light rays together at a focal point, and a concave lens spreads them outward.
It's all about how that curved shape manipulates the path of light.
Exactly.
Okay, I'm starting to see how this all connects.
Great.
So if a convex lens converges light, does that mean it can magnify things?
Exactly.
Like those concave makeup mirrors we talked about?
Yes. Think of a magnifying glass.
Uh-huh.
That's a classic example of a convex lens in action.
Oh, yeah.
When you hold it over an object, it bends the light rays from the object inward,
Okay.
converging them at a point,
Right.
which creates a magnified image on the other side.
So it's gathering all that light from the object
Yes.
and concentrating it into a bigger image. That's so cool.
It is pretty neat.
Yeah.
And this principle allows us to see tiny details that would be invisible to the naked eye. Like, think of microscopes.
Oh.
They use a series of convex lenses
Uh-huh.
to magnify objects hundreds or even thousands of times.
Wow. Okay, so convex lenses are all about making things appear larger. But what about concave lenses? Where do they fit into the picture?
Well, concave lenses, with their diverging nature, are often used to correct nearsightedness.
Okay.
People who are nearsighted have difficulty seeing distant objects clearly because their eyes focus the light in front of the retina instead of directly on it.
So a concave lens helps spread the light out a bit so it hits the retina correctly.
Precisely by diverging the incoming light rays, a concave lens essentially pushes the focal point back, allowing the nearsighted eye to focus properly.
It's a clever way to use refraction to correct vision problems.
Is.
Lenses are truly fascinating.
They are.
From magnifying tiny objects to helping us see the world clearly.
Yeah.
Now, I remember you mentioned that the strength of a lens is measured in diopters.
Yes.
Can you explain what that actually means?
Of course, the diopter is simply a unit of measurement for the optical power of a lens.
Okay.
It tells us how strongly the lens converges or diverges light.
Okay.
A higher diopter means the lens has a stronger bending power.
So my eyeglass prescription with all those plus and minus signs,
Yeah,
those are diopters.
exactly. The plus sign indicates a convex lens,
Uh-huh.
which converges light,
Okay.
while the minus sign indicates a concave lens,
Right.
which diverges light.
Okay.
The higher the number, the stronger the lens.
So someone with a prescription of plus 2.00 has stronger convex lenses than someone with plus 1.00.
That's right. And those numbers are carefully calculated by an optometrist
Right.
to ensure the lenses provide the right amount of correction for your specific vision needs.
It's amazing how something as simple as a curved piece of glass
I know, it's incredible.
can have such a big impact on our ability to see.
It really is, and the applications of lenses go far beyond just vision correction.
Oh, right.
Like, think about camera.
Cameras. I've always wondered how those lenses actually work.
Well, a camera lens is essentially a convex lens, or sometimes a combination of lenses,
Okay.
that gathers light from a scene
Uh-huh.
and focuses it onto a light-sensitive surface.
Okay.
Either film in traditional cameras or a digital sensor in modern cameras.
So the lens acts like a funnel, capturing all that light and directing it to a specific spot.
That's a great analogy.
Okay, cool.
And the size of the opening in the lens,
Yeah.
called the aperture, controls how much light gets in.
Okay.
A wider aperture lets in more light, which is helpful in low light conditions, while a narrower aperture restricts the amount of light
Okay, makes sense.
that enters the camera.
And I've also heard of focal length when it comes to camera lenses.
Yes.
What does that mean?
Focal length is the distance between the lens
Okay.
and the point where it focuses the light
Uh-huh.
to create a sharp image.
Okay.
It determines the field of view, how much of the scene you capture, and the magnification of the image.
So a shorter focal length means a wider field of view,
Yes.
like for landscapes.
Exactly.
While a longer focal length gives a narrower view, but with more zoom,
Yes.
like for wildlife photography.
You got it. Photographers use different lenses with varying focal lengths to achieve different creative effects and perspectives.
It's incredible how much control a photographer has over the final image just by choosing the right lens.
Absolutely. And the science of optics plays a crucial role in making it all possible.
From eyeglasses to microscopes to cameras.
Yeah.
Lenses are all about manipulating light to enhance our vision and capture the world around us.
Exactly.
Now, speaking of seeing the world, I can't help but think about telescopes.
Okay, telescopes.
They're like superpowered lenses,
Right.
allowing us to peer into the vastness of space.
Eh.
How do those lenses work to bring distant stars and galaxies into view?
Telescopes are truly remarkable instruments, and the principles behind them are similar to what we've been discussing with light.
Okay.
Let's take the refracting telescope as an example. It uses two main lenses, the objective lens and the eyepiece.
Okay, so where do those lenses fit in?
The objective lens is at the front of the telescope, and it has a large diameter to gather as much light as possible from distant objects.
Oh, okay.
The bigger the objective lens, the more light it can collect and the fainter objects it can detect.
So it's like a giant light bucket scooping up those faint rays from distant stars.
Exactly. And this objective lens then focuses the light to a point inside the telescope's tube,
Uh-huh.
creating a real inverted image of the distant object.
Wait, so we have a tiny upside-down image of a star floating inside the telescope.
Yeah.
How do we actually see it?
That's where the eyepiece comes in.
Okay.
The eyepiece is a second lens,
Yeah.
usually with a much shorter focal length than the objective lens.
Okay.
Its job is to magnify that real image created by the objective lens, making it appear larger and easier for our eyes to see.
So it's a double magnification process.
Yeah.
First, the objective lens gathers the light and forms a real image.
Yeah.
Then the eyepiece magnifies that image further.
That's a great way to put it. And by adjusting the distance between the objective lens and the eyepiece, you can fine-tune the magnification and bring those distant objects into sharp focus.
It's mind-blowing to think that we can see objects millions of light years away,
Yeah.
all thanks to these carefully crafted lenses.
It really is. Telescopes are powerful testaments to our understanding of optics, allowing us to push the boundaries of our knowledge and explore the cosmos in ways that were once unimaginable.
Now, we've talked about light bending when it passes through different materials.
Right.
But what happens when light hits a surface that doesn't allow it to pass through like a mirror?
Yeah.
Where does the light go?
That's an excellent question, and one that leads us to another important concept in optics absorption.
Okay.
When light strikes an opaque surface, meaning it doesn't transmit light,
Ah,
some of the light energy is absorbed by the material.
okay. So some of the light gets soaked up, but what happens to that absorbed energy?
It's typically transformed into other forms of energy, most commonly heat.
Oh, okay. That's why dark-colored objects tend to get warmer in sunlight than light-colored objects. They absorb more light energy.
So that's why black asphalt gets scorching hot on a sunny day.
Exactly.
It's absorbing all that light energy and converting it into heat.
That's right. And the amount of light absorbed depends on the material's properties and its color.
Okay.
Darker materials absorb more light across a wider range of wavelengths, while lighter materials reflect more light.
So when we see an object's color, are we actually seeing the wavelengths of light that are reflected, not absorbed?
That's exactly right. The color we perceive is determined by the wavelengths of light that bounce back to our eyes.
Okay.
For example, a red apple appears red because it absorbs most wavelengths of light except for those in the red part of the spectrum, which are reflected.
So the world of color is really all about which wavelengths of light are absorbed and which are reflected.
That's a beautiful way to put it.
It's like a selective process where each material chooses its own color palette. The interaction between light and matter is incredibly complex and multifaceted, leading to the stunning diversity of colors we experience in our world.
Well, my mind is officially blown. We've covered so much ground today.
We have.
From the basics of reflection and refraction to the mind-boggling applications of lenses in everything from eyeglasses to telescopes.
Well, quite a journey.
I feel like I have a whole new appreciation for the power and magic of light.
It's been a fantastic journey exploring the world of optics, and I hope our listeners are feeling just as inspired and enlightened as you are.
Before we wrap up, is there anything you'd like to leave our listeners with to ponder as they continue to observe the wonders of light in their everyday lives?
I'd encourage everyone to look around and really pay attention to how light interacts with the world around them. Notice the reflections in windows and puddles, the bending of light in a glass of water, the way different materials absorb and reflect different colors. There's a whole universe of optical phenomena waiting to be discovered right in front of our eyes.
That's a great reminder. The world is full of optical wonders just waiting to be explored.
It is.
And with a little understanding of the science behind it all,
Yeah.
those everyday experiences become even more fascinating and awe-inspiring.
Absolutely.
It's amazing to think that something as fundamental as light
I know, right?
is responsible for so much of what we experience and understand
Yeah,
about the world around us.
absolutely. Light's not just what lets us see, it's also a carrier of information,
Oh, for sure.
energy, and a source of endless fascination.
Speaking of fascination, today's deep dive
Yeah.
has really illuminated some, mind-boggling concepts.
It has.
We started by unraveling the mystery of rainbows.
Right, those captivating displays of color that we see after a rainstorm.
We saw how the interplay of reflection and refraction
Yes.
within those tiny raindrops
It's amazing.
separates sunlight into its colors,
Yeah, creating that breathtaking art.
creating that art.
Huge
Then we delved into the world of mirrors.
mirrors.
Yeah, exploring how those curved surfaces
Right.
can either converge light to magnify objects
Yeah.
or diverge it to expand our field of view.
Exactly.
We learned how concave mirrors are used in everything,
Right?
from makeup mirrors to car headlights,
Yeah, all sorts of things.
while convex mirrors give us that wider perspective
Exactly.
in car side mirrors
Yes.
and security cameras.
Yeah.
And then we went into the realm of lenses.
Lenses, those ingenious pieces of curved glass
Yeah.
that harness
You
refraction.
do some remarkable things.
They really do.
We discussed how convex lenses converge light
Yeah.
to magnify objects,
Right,
making them essential in magnifying glasses, microscopes,
Yeah.
and cameras.
And we saw how concave lenses can correct nearsightedness
Yeah.
by adjusting the focal point.
Yeah, by pushing the focal point back.
Exactly.
We even journeyed into space,
Space, the final frontier.
discovering how telescopes,
Yeah.
with their carefully crafted lenses,
Yes.
extend our vision
Beyond our naked eyes.
to witness the wonders of distant stars and galaxies.
It's incredible, isn't it?
It's mind-boggling to think that everything we see,
Yeah.
every color, every image,
Right.
is a result of how light interacts with matter.
The study of optics really unlocks
Yeah,
a deeper understanding of our visual perception.
for sure.
It reveals this intricate dance between light and the physical world.
Well, I feel like our deep dive today has,
Yeah.
shed light, pun intended,
Haha. I see what you did there.
on a subject that's often taken for granted.
I hope our listeners have gained a newfound appreciation
Yeah.
for the role that light plays
For sure.
in shaping our understanding of the universe.
Before we sign off, I want to thank you for sharing your expertise with us today.
It's been my pleasure.
It's been an illuminating journey.
I always enjoy exploring the world of light
Yeah.
and sharing that passion with others.
And to our listeners,
Yes.
keep those curious minds engaged. The world is full of optical wonders waiting to be discovered.
It really is.
Pay attention to the play of light and shadow,
Yeah.
the reflections in everyday objects, the way colors shift and change
Right.
under different lighting conditions.
Remember, every time you see a rainbow or snap a photo
Ah.
or just gaze at the stars,
Yeah.
you're witnessing the power and beauty of light.
So keep exploring, keep wondering,
Yes.
keep diving deep
Deep diving deep.
into the mysteries of the world around you.
Absolutely.
Until next time, this has been The Deep Dive.
Thanks for listening, everyone.